Okay, so we are going to talk about how to graph exponential functions. And in this activity, we're going to start looking at how the different parts of the general form adjusts the graph. So the first thing I want you to take a look at is this equation right here, this format. Okay, this is the exponential function general form. And what we have is f of x, or y, equals a times b to the x power. This looks very similar to our explicit rule for geometric sequences. So keep that in mind as we work through this. So we want to find the effect of b in this first section. Graph the functions with different colored pencils. You'll use the graph to determine the effect of b greater than 1 on an exponential function. Okay, so we're going to be looking at what happens when the b is greater than 1. And remember, our b is the number that's the base of the exponent. Okay, so in number 1, we're first going to identify each part of this format. Okay, so we're going to identify the a and the b. Now, we don't see any number being multiplied by the b here. So if we don't see a number being multiplied, it's always a 1, right? So really what this equation is 1 times 2 to the x power. Okay, so keep that in mind, that even though we don't see the a, that doesn't mean there isn't one. So our a is 1, and in this case, our b is a 2. So we're going to go through and we're going to complete a table, because with exponential functions, the way the graphs are, at least while you're starting out, it's easier to create a table for your graphing. So off to the side, I'm going to do the work. So I'm going to replace the x with a -1. And hard for our brains to try to comprehend with the negative exponent. If you have a calculator, you can use that. But ultimately, I'm going to use our power rules. And I'm going to say that, well, I don't really know how to handle that -1 and find the value. So I'm going to rewrite this as 1/2 to the first power using that negative exponent rule. And ultimately, what that ends up equaling is 1/2 or 0.5. So then 2 to the 0 power. Anything to the 0 power is 1. 2 to the first power is obviously 2. Anything to the first power is itself. And 2 to the second power is 4. So then we're going to go down to our graph. And we're going to plot our points. So remember that the x and the y, we're creating ordered pairs in our table. So my first ordered pair was x is -1, y is 1/2. So do your best to get as close as possible. 0, 1, 1, 2, and 2, 4. Now this is going to create a curve, and it is hard to have a nice perfect curve, so just do your best. As long as your curve goes through those points, you're okay. Don't go crazy and start drawing off this left side, because eventually we're going to see that there's something very specific that happens on that end. Same thing here. Don't just go crazy drawing straight up, because we didn't really see exactly what happens from here, and we see it's a curve, and we just haven't done this enough to have an idea of what happens to that curve as it goes up. So we're just going to stop there for now, and we're going to label our graph with the equation, just so that in the next part we can kind of see what happened. Okay, so head back up to number 2, and we're going to repeat the process. So our a is still a 1, because if there's no number being multiplied, we know it's 1. But this time my b is a 3. Right? It's my b. So again, same type of process. 3 to the negative first power is going to be equivalent to 1 over 3 to the positive first power. So 1/3. 3 to the 0 power is still 1. Anything to the 0 power is 1. 3 to the first power is 3. And 3 to the second power is 9. Now, before we go graph, I want to stop for a second and talk about what's happening in both of our tables. So there is a pattern within our y coordinates that I want to quick talk about. Now, this pattern only works when our x's are increasing by 1. Okay, so if our x values were all over the place, this doesn't work the same. This works when our x's increase by 1. Okay, doesn't matter where you start your x's, but as long as they increase by 1 every time, this follows. So it might be kind of hard to see from the 1/3, but if we go from the 1, if I look at my pattern, as my x's increase by 1, my y's actually follow a geometric sequence. This is 1 times 3 is 3. 3 times 3 is 9. I can even back it up. 1/3 times 3 is 1. 1 times 3 is 3. 3 times 3 is 9. So this follows a geometric sequence. If we look at our first table, 0.5 times 2 is 1. 1 times 2 is 2. 2 times 2 is 4. So that also follows a geometric sequence. And if you think about it, every y is getting doubled, and my b is a 2. If we look over here, every y is being multiplied by 3, and my b is a 3. If we look back up here, this is very similar to our geometric sequence explicit rule, which was the first term, right, times the ratio to the n minus 1 power. Oops. It's very, very similar in that the base of the exponent is the ratio. And if we look down here, my base was a 3 and my ratio was 3. Over here, my base was a 2, my b is a 2, and my ratio was a 2. That's kind of interesting, right? So let's look at 3. So we're going to try to do the table for 3 following what we just saw, where we have a geometric sequence. Okay? And there's something else we're going to do too in just a second. So let's label our A is still 1, and our B is now 4. Now we can see that the 4 will be the ratio, so we're going to be multiplying by 4. Okay, but for our first term, that somehow that aligns up with the A in some way if we kind of look here. So this A might have something to do with the first term, but ultimately we need some place to start, right? And according to what we've done so far here, when we had a 0 power, we ended up, when our x was 0, we ended up with a y of 1. So I'm just going to test that out really quick here. 4 to the 0 power, right? And that does equal 1. And then from here, I can use my geometric sequence, knowing that my ratio is 4, and I know that I'm going to say 1 times 4 is 4. 4 times 4 is 16, right? If I back it up, this would have to be 1/4, because 1/4 times 4 is 1. All right, so we did not graph number 2 yet, so we're going to graph 2 and 3 at the same time. All right, so go ahead and get number 2 graphed. So we have negative 1 and 1/3, and just do your best to get as close as you can there. Negative or 0, 1, 1, 3, and then 2, 9. Now this is going to be a little bit trickier to draw. Just do your best, go point to point, and do your best to kind of curve it. It's not going to be perfect. So y equals 3 to the x power. And again, I'm not going to go too crazy down here just because we haven't really seen exactly what happens. And then number 3, we're at a fourth, just somewhere down here. Then we have 0, 1. Then we have 1, 4, and 2, 16. And again, not going to look great, but you get the point. So there might be some things you start noticing, and that's good. The point of this whole thing is to start noticing patterns. All right. So the one pattern that we do want to talk about though is the B. So the goal for this section was to try to figure out how the B affects our graph, and B greater than 1. So when B is greater than 1, what can we say about the y-intercept of our graph? What can we say about the end behavior? And the y-intercept might be affected by the B, it might not, but we want to talk about it anyway because something has happened on this graph. And you probably noticed the y-intercept has been 1 every single time. It might be because of the B, it might not, but we're still going to make a note because they want us to talk about the graph. So the y-intercept are 1. So our y-intercepts are 1. Now remember, the end behavior basically says, or basically means from left to right, what's happening in the graph. Is it increasing? Is it decreasing? What's the trend, or what is happening? What's the behavior from left to right? And if we look, our curve is increasing from left to right. Starts low, goes high. So our curve is increasing. Now you can also say growing, because when we have exponential functions, we see a growth and a decay. We could also say like it curves up, or any other kind of observations you can make about what's happening here, definitely write down. Doesn't have to just be about the B greater than 1. It can be any observations. The more observations you can make, the better. Okay. So next page. Same type of process, except now instead of having numbers where the B is greater than 0, we now have B's that are between 0 and 1, fractions. So let's identify our A and our B again. My A is still 1, right? Because if I had a number multiplied by this power, it would be a 1. And the B is 1/2. So now thinking about what we just saw on the other page, we can start having the idea that, okay, well, the ratio is probably 1/2. My numbers are probably going to be divided by 2 on my y's. Because remember, my x's are increasing by 1. So if we have a geometric sequence here, this ratio is going to help us decide our next points. But just to be sure, we're going to Do a little bit of math, at least on this one. We can skip the math on the others. This is good practice for exponents anyway. So for x is -2, the power of a power rule tells me that this becomes 1 to the -2 over 2 to the -2. To avoid those negative exponents, I'm going to take this 1 to the -2 and I'm going to make it 1 to the +2, but it'll be in the denominator position. Because remember, it moves from the denominator to the numerator or the numerator to the denominator. So 2 to the -2 is going to move up to the numerator and become 2 to the +2. So I get 4 over 1, which is 4. Now we can start anticipating my ratio is 1/2, so there's a good chance that if I multiply 4 by 1/2, I would get 2. So in our head, kind of anticipate that that's going to be a 2. But we're still going to do this math. It's good practice, and we're just doing that to be sure that this pattern still follows. So my 1 to the -1 is going to move to the denominator and become 1 to the first. 2 to the negative first power is going to move to the numerator and become 2 to the positive first. And then I end up with 2. And yes, this follows that pattern. So I can now assume that I'm going to cut 2 in half and get 1, and cut 1 in half and get 0.5. And then let's go ahead and graph it. And we get a curve again. Now make sure you're being very careful about putting that 1/2 in parentheses, because the whole 1/2 is the base. If you leave those parentheses out, 1 is the only thing to the exponent there, or with an exponent of x. So be very, very conscious of that. All right, so let's do number 6 on the table. My a is still 1 because there's no number out here being multiplied, so a 1 is hiding out there. And my b is 1/3. Now, if we take a look over and see what happened here, on the front side, when our x was 0, our y was 1, because anything to the 0 power is 1, right? So on this side, if my 1/3 has a 0 power, that's going to equal 1. Anything to the 0 power is 1, right? So it's a little bit faster for me to fill out that part of the table. My ratio is 1/3, so 1 is going to be cut into thirds. Now, if I back it up a little bit, this would have to be 3, so that when I multiply it by 1/3, I get 1. This would have to be 9, so that when I multiply it by 1/3, I get 3, right? And again, we have geometric sequences happening here. You can go through and do the math with your exponents, or start using the skills that we have been learning about geometric sequences and from these tables, and just start being more efficient. So let's go down and graph those. This is y equals 1/3 to the x power. And I know my line started looking straight here, but it is supposed to be curved. So keep that in mind. And then let's do number 7. A is 1, B is 1/3. So now let's notice again that when my x is to the 0 power, when my x is 0, my y is a 1. That should follow here as well. Now remember, when I talked about the geometric sequence, the explicit rule, it was first term times the ratio to the n minus 1, right? Well, from what it looks like here, my a's are always 1, and when x is 0, my y is 1. So we can kind of look at this a as our first term. And I know, with a sequence of numbers, your first term is the first number listed. And that's not happening here. But if you think about when we graph lines for linear equations, we always started at the y-intercept, didn't we? So since we always started at the y-intercept, that's kind of our beginning. And so we can kind of consider x equaling 0 as our beginning or our first term. So that's something to kind of think about. And if we look here, our y-intercept has been 1 every time. On our other graph, our y-intercept was 1 every time. So there might be something to that. We'll see it a little bit more in the next part, but kind of let that roll around the back of your head a little bit. So if I follow, oops, that's not supposed to be 1/3, that's 1/4. Hopefully you caught that and fixed it. So if my ratio is 1/4, that would be 1/4. If I back it up, this would have to be 4 and 16. Now, if you go through and do this, just double check with your ratio that you're doing your math right. 16 times 1/4 is 4, 14 times 1/4 is 1, 1 times 1/4 is 1/4. And then let's graph. See if I can get the whole thing in there we go. All right, now this one's tough to draw because we're going kind of backwards. Oh, shouldn't have done that, but it should not have crossed over here. But I think you know what we're doing here. Right. Sorry about that horrible second one. This pink one was rough. All right, so now we can start talking about our questions down here. How does b being between 0 and 1 affect the graph of the equation? Okay, so if we compare our two equations here, see if I can get them both in the picture. This was when our b was greater than 1. This is when our b was between 0 and 1. And if you look, they're basically mirror images of each other, right? Our y-intercept was still 1. If you look, this is x, y equals 4 to the x power. This is y equals 1/4 to the x power. Y to the third, or y equals 3 to the x. Y equals 1/3 to the x. So there's some interesting things happening here. Our y-intercepts are still 1. So we're going to make a note down here that our y-intercepts and our b changed, but our y-intercept stayed 1. So there's a very good chance that the b has nothing to do with the y-intercept. Okay, because the graphs obviously changed, but the y-intercept stayed the same. Now the end behavior, our lines are now decreasing. So from left to right, they're decreasing, curving down, right? Not our line, our curve is decreasing. Or decaying. It's curving down, right? Now, number 9 says, use the graphs to make a conjecture. Now, we're going to skip the domain and range part for now. We're going to come back to that in a couple activities. But I do want to make an observation about our two graphs. So when b was greater than 1, if we look here, I want to talk for a second about what happens as the b gets larger over here. So as my b gets larger, we can say that the curve gets steeper. But over here, as our b gets larger, the curve gets flatter. Remembering that 1/2 is larger than 1/4, right? So putting it in those words doesn't really work. But there is something happening as these b's change. So something that you could say is, as the b gets further away from 0, does it get steeper? No, that doesn't happen, right? As the b gets further away from 0, that doesn't get bigger. So maybe we have to say, if b is greater than 1, the larger it is, the steeper it gets. If b is between 0 and 1, the smaller it is, the steeper it gets. Okay, so there's a chance that in this case, we have to find a different way to put it. Okay, so we're just gonna make a note down here that if b is greater than 1, as b increases, the curve gets steeper. If b is between 0 and 1, as b gets smaller, the curve gets steeper. Okay, so again, we're just trying to find as many observations as we can to help us understand how these numbers change our graphs.